Oh, sorry about that. That's fine. Definite integral of a continuous function. Working our way, and we'll be there soon, to use the idea of an antiderivative to calculate the area bounded by a curve and the x-axis. Ultimately, we can use this to find the area in between two curves. But for most of the examples that we'll use, it'll be the area bounded by the curve and the x-axis. So let's see if we got a picture to go with this. Suppose a continuous function f. Continuous function maybe, let's see, here's a, and here's b. And the function there is defined at a, and it's defined at b. And it does something like this. It doesn't have to be a nice smooth curve, but oftentimes we think of these continuous functions as also being smooth. So suppose a continuous function takes on, whoa, well, I've already messed up the picture. Both positive and negative values. So I've got to redraw it. Maybe I could just extend it a little bit. No, actually, if I erase this, I'm going to have to redraw it. Both positive and negative values. So let's do this, and then dip down below, and then it doesn't have to come back up, but let's say it does. On the closed interval from a to b. Then there will be regions both above and below the x-axis, which are bounded by the curve y equals f of x and the x-axis, as indicated in the graph below. Okay, here it is. Call this region 1, call this region 2, and call this region 3. There they are. Above the x-axis, 1 and 3. Below the x-axis, region 2. Shrink this down a little bit so I can fit this to the side. The total, I shouldn't use the word total. If I take the area of region 1 and add it to the area of region 3 and then subtract the area of region 2, or maybe I should say it like this. Area 1 minus area 2 plus area 3. This is called the net signed area of the region of the regions bounded by the curve and the x-axis. It's typically less than the sum of the areas, because if any one of them is making a negative contribution, that's going to be subtracted from the total rather than added to the total. We've used the expression with the integral sign to this point to denote an antiderivative. We've called this integrating a function, and we look at little f and we ask ourselves, what function could we differentiate to get that as the answer? And a function that we can differentiate to get f of x as the answer is called an antiderivative. We want to expand on this notation. This is called an integral. If we put a little a down there, call that the lower limit of integration, and a little b up there, and call that the upper limit of integration. This is called a definite integral, or the definite integral of the function f from a to b. And if we evaluate this, basically, if it doesn't have a little a and a little b, the limits of integration, it's going to give us a function, an antiderivative that we can take the derivative of to get this. But if I put the little a and the little b on it, it doesn't correspond to a function. It corresponds to a number, a value. It's the net signed area bounded by the curve in the x-axis. So for this particular function, the integral from a to b of f of x dx is equal to the area of region 1 minus the area of region 2. It makes a negative contribution because it's below the x-axis, plus the area of region 3. We just have to be careful when we use, because what we're going to do in a little bit is we're going to use an antiderivative. It kind of shares the same notation, because we're going to be able to use an antiderivative to evaluate this expression and actually calculate the area. We just have to know if it dips below the x-axis, as it does in this picture, not the total area. We might need the total area, or we might just need the net signed area, but it's just giving us the net signed area when we write this. We're going to use the fundamental theorem of calculus and an antiderivative of the integrand to come up with the area, the net signed area. Here's the fundamental theorem of calculus, part 1. If f is continuous on the closed interval from a to b, and if big F is any antiderivative, we find the antiderivative like we've been doing, then the value of this definite integral can be found by doing this. It seems, well, to me at least, for the longest time until I saw a serious proof of this, it seemed almost too good to be true, almost too easy. Because to find the area of that total region, the net signed area, all we have to do is find an antiderivative, evaluate it at b, evaluate it at a, and subtract. Any antiderivative will do. Antiderivatives differ by a constant, but since we're going to take the same antiderivative and evaluate it at the upper limit and evaluate the lower limit, those constants, whatever they might be, would cancel each other out. So it's best to keep it simple and keep the constant 0 if we can when we're choosing an antiderivative to use to do this. Let's see how it works with example 1, and then we'll compare, we'll see if we can get GeoGebra to come up with a numerical approximation of this, and we'll see the difference, if any. So the integral from 1 to 3 of 6x squared dx. Well, we should use a power rule rather than just kind of staring the thing down and asking ourselves, what can we take the derivative of to get 6x squared? Although that's not a bad question to ask. The power rule went something like this. We take the exponent, the 2, and we add 1. So we get 6x cubed. And then we take the new exponent that we got, the 3, and divide by that exponent. 3. Now I'm not getting a function here. I'm not getting an expression. I'm getting a number. So I'm going to write some notation that we can use to evaluate this. I'm going to put this in brackets. I'm going to put it in brackets and take the 1 and put it right there, and take the 3 and put it right there. What that means is take this expression inside the brackets, plug in the 3, plug in the 1, and subtract. That's what the notation means. So I'll simplify it. It's 2x cubed, right? 2x cubed is an expression that we could take the derivative of and get 6x squared. Sure, that's an antiderivative. 2x cubed plus any constant will work, but let's let the constant be 0. Now, we want a number, not an expression. We want a number. So take the 3 and evaluate the expression there. 2 times 3 cubed. Take the 1 and evaluate the expression there. 2 times 1 cubed. And subtract. I want to say that's 54. Does that look like 54? 27 times 2 is 54 minus 2. That's 52. I think this function, in fact I'm pretty sure it's only positive between 1 and 3. This is going to be the actual area bounded by the curve 6x squared and the x-axis on this interval. Well, let's look at an approximation for it. I'm going to type in y equals 6x squared. And we're going to go from 1 to 3. And maybe zoom in just a little bit on that. Scoot it over where we can see it. Okay, so we're familiar with the parabola y equals 6x squared. If we wanted to come up with an estimate of the area, what we could do is draw some rectangles. Here I have GeoGebra drawing 5 rectangles, and it calculates the area of all 5 of those rectangles. This one, this one, this one, this one, this one. Adds all those areas together, and it comes up with 61.92. which is a pretty lousy estimate of the actual area. You can see what's in green here, right here, right here, right here, right here. That's overestimating it. Now what we can do is kind of scoot those rectangles a little bit. See if I can successfully scoot them. Maybe I'm not scooting the rectangles, I'm just kind of lowering the rectangles so the height of the rectangle is right in the middle of the top of the rectangle rather than at the left or at the right. If I do it like this, then what you see in green right there overestimates the area bounded by the curve on that little interval. And what you see, and I guess that's pink or pinkish orange, something right in there, that underestimates it, so they kind of cancel each other out, not exactly, but close. And so the estimate is actually a pretty good one. So if we take those 5 rectangles and add up their areas, it's 51.84. Now, if we were to put more rectangles and skinnier rectangles in there, what would happen is that the green parts and the orange parts would come closer and closer to canceling each other out, and the sum of the areas of those rectangles would get closer and closer to the actual area underneath the curve. So I'm going to grab the slider for the N and go with more rectangles. See there, we've got 16 rectangles, and it's a really good approximation, 51.98. If we drag that across there, more and more rectangles, that's about 103 rectangles. Really, really close. If we add up the areas of all those 103 rectangles, it's really close to 52. So we're saying that the actual area bounded by the curve in the x-axis is exactly 52. Okay. But we get that by finding an antiderivative, plugging in the upper limit, plugging in the lower limit, and subtracting. That's what we do there. Let's try it with example 2. Example 2, find the net side area bounded by the graph of f of x equals negative 4x cubed plus 16x and the x-axis between negative 1 and 2. Now we might want to see what this looks like. I'm going to use a more conventional method, the TI-84, plus graph it, and I believe it does dip below the x-axis. It might be completely below the x-axis on that interval, but hopefully to illustrate my point, it will at least go below the x-axis. That's pretty close. That's not it, though. Negative 4x cubed, okay, so it wasn't that close, plus 16x. And I left off the negative side. What's a good viewing window? I'm thinking this is going to be way too high, way too low, but I'm going to zoom 6 nonetheless. We're just going from negative 1 to 2. So between negative 1 and 2, it doesn't go a whole lot higher than 10 or a whole lot lower than negative 10. Let's do this. Let's say maybe from negative 4 to positive 5, and from negative 20 to positive 20, and a y-scale of 5, and see if this graph gives us a good indication of what's going on. Maybe I can shade different regions here. There we go. So it's from negative 1 to 2. If I take that, we can see the portion that's above the x-axis and the portion that is below the x-axis. Here is negative 1. If I shade that, it's going to calculate this area. And from 0 to 2, that looks like that's completely above the x-axis there. From 0 to 2. So that's going to make a positive contribution. If we find, so let's call this, what should I call this? Area 1, I guess. All right, so much for the shading. Area 1. And so much for the shading here. Let's call this area 2. If I calculate the definite integral from negative 1 to 2 of negative 4x cubed plus 16x between negative 1 and 2, it's going to give us the opposite of area 1 plus area 2. It's not going to be the total area bounded by the curve, not the sum of those areas, but whatever area 2 is, it's going to subtract from that area 1, and it's going to give us that answer. So let's see. We need an antiderivative. What can we take the derivative of and get negative 4x cubed? Negative 4x to the 4th over 4 would be good. So I guess just plain old negative x to the 4th. Take the derivative of negative x to the 4th. That's negative 4x cubed. Yeah, that'd be fine. Plus, what can we take the derivative of and get 16x? Would you believe 16x squared over 2? Or maybe 8x squared? Take the derivative of 8x squared. Should we try it with your favorite constant? Toss in a constant here. Someone pick a number from 1 to 10. I don't know, maybe your favorite constant's not between 1 and 10, but let's just 3. 3? Okay. So plus 3. Any antiderivative will work, so we're going to go with that one. Going to go from negative 1 to 2. We'll simplify a little bit. So it's going to be negative x to the 4th plus 8x squared plus 3. And we're going to go from negative 1 to 2. This notation means take the 2, plug it in. Take the negative 1, plug it in, then subtract. That's what we'll do. So it's going to be parentheses, probably going to help here because of all these terms. The negative of 2 to the 4th plus 8 times 2 squared plus 3 minus the negative of negative 1 to the 4th plus 8 times negative 1 squared plus 3 equals. Take the 2, plug it in, take the negative 1, plug it in, subtract. We're going to get negative 16 plus whatever 8 times 4 is, that's got to be 32 plus 3 minus the opposite of 1 plus 8 plus 3. If I write out all these terms, is it so far so good, or is there an issue? I think rather than simplify inside each set of parentheses, I'm going to clear the parentheses so it's clear what happens with the 3 and the minus 3. Negative 16 plus 32 plus 3 plus 1 minus 8 minus 3. See what's going on with our favorite constant, 3? It gets canceled. Yes, it gets canceled. What happened? Oh, we're looking for the final answer. What is the final answer? 16 plus 1, 17 minus 8. What's 17 minus 8? 9. Is it 9? All right. For that one, I need a different GeoGebra worksheet. Hopefully this one will work because it's the area between two curves. Open. Sure, save it. Why not? Area between two curves, which if I let the bottom curve be the x-axis, it would work just as well as the area bounded by a curve in the x-axis. So if we let our function, I don't see where it's letting me type in the function. I guess it's right there. Let that be was it negative x to the 4th? No. It was negative 4x to the 3rd plus 16x. Tell me that's what it was. A bigger font here. See things a little bit better. All right, but we don't want to go from 4 to 10. We want to go from negative 1 to 2, like that. Okay, so it does a calculation and agrees with our 9. The exact net signed area is 9. And just with these few rectangles that we have here, the approximate net signed area is 9.375. A few more rectangles, I think we can get that closer to 9. So let's go grab the n. This is the number of rectangles, and zoom in on that so we can see what's going on. With 30 rectangles, it's 9.015. That's pretty close. How about with about 125 rectangles? That's as close to 9, I think, as it needs to be. So the exact net signed area is 9. The total area bounded by the curve and the x-axis is not 9. It's 23. 23. If we take the area of region 1 there, down there, and the area of region 2, and we add those areas together, it's actually 23. It's when we take and subtract, find the difference in the areas, then it's just 9. Just important to know what the antiderivative tells us. If we had wanted a function where the net signed area was 23, we would need to do this. Absolute value. I'm not sure if GeoGebra is going to let me do this, by the way, but I'm going to hope it will. It might give me some error. Invalid input, probably is what it'll say. No, it did it. When you take the absolute value of an expression, whatever portion of it is above the x-axis stays put, and whatever portion is below the x-axis gets reflected about the x-axis. So the portion that was negative got reflected about the x-axis. So now, however much is here makes a positive contribution. How much of the area is between -1 and 0? Let's see. There's about 7 units right there. We probably could have done some basic algebra and come up with that. So if there's 7 right there, how much is there between 0 and 2? About 16 right there. If we take the 7 and add the 16, we get 23. If we take the 16 and subtract the 7, we get 9. But it has to be above the x-axis to make a positive contribution for the definite integral. All right. Both of these, I think, are going to be above the x-axis wherever we need them. We can compare with GeoGebra and see, but I think this is going to work out okay for us. The integral from 0 to 2 of e to the x is going to be, well, what's the antiderivative for e to the x? Well, if it were a difficult problem, it might be e to the 5x, 5kx, sure, why not? E to the 5x, then we'd have to go with, 1 over 5 e to the 5x. But this one's not difficult. We don't have to divide by 5. All we have to do is copy and paste. We know if we take the derivative of e to the x, we get e to the x. So e to the x is one of its own antiderivatives. So this one's short and sweet. Take the 2, plug it in, get e squared. Take the 0, plug it in. Oops, it's supposed to be a minus sign. Take the 0, plug it in, and get 1. So this is going to be e squared minus 1. E squared is 7 point something. We subtract 1, we get 6 point something. But it's completely above the x-axis. So if we go here, I want area between two curves. It's kind of curious because I don't know where the second curve will be. Fortunately, it doesn't matter. If I just put in e to the x and integrate between 0 and 2, e squared minus 1 is about 6.389. So squiggles, 6.389. Integral from 1 to 5 of 1 over x. This is the special one where the power rule doesn't work, right? If we have the integral of x to the negative 1 dx, and we try to say x to the negative 1 plus 1 over negative 1 plus 1, we have issues because that causes a division by 0, and we don't want that, so we can't use the power rule. But what can we do? Take the derivative of what? You get 1 over x. The natural log. So, going to use natural log, and we want to evaluate it at 5, evaluate it at 1, and then subtract. So this is the natural log of 5 minus the natural log of 1. And the natural log of 1 is 0. So this is the natural log of 5 minus 0. So it's the natural log of 5. So if we have this function, the reciprocal function, goes through 0.11 and 2 1/2 and 3 1/3 and 4 1/4, and does this like that. This particular one, we just went out to 5. But if we go to 5, from 1 to 5, the area is the natural log of 5. The area there. I know. I should use this to draw a better picture, huh? 1 over x. Looks like that. But just go from 1 to 5. And it does like that. It's tough. I can't really zoom in on it. I think I can do this though, like that. See a little bit better. So evidently the natural log of 5 is 1.6. What do you think? Natural log of 5? Natural log of 5 is about 1.6. There it is. And it's something that we have an application. Let's see if we can make sense out of this. Marginal cost in dollars of printing a poster when X posters have been printed, given by the following equation. C prime of X equals X to the negative 6/7. As we know, the marginal cost is the derivative of the cost function. What we want here is a way to evaluate the cost function and find the total area bounded by the cost function and the x-axis. So the total cost for printing posters 15 through 160. So if I knew what the cost function was, let's see. The integral, I'm concerned about the limits. I'm going to go ahead and say 15 through 160. I'm a little concerned that might not give me $4.15 though, so we may need to correct that a little bit. C prime of x dx, this is going to be the integral from 15 to 160 of x to the negative 6/7 dx. Going to add 1 to the exponent. How about multiply by the reciprocal of the new exponent that we get? So it's going to be x to the 13/7. If I add 7/7, no, that's terrible. How did I do that? Let's try that again. What is negative 6/7 plus 7/7? That's actually equal what? 1/7. Yes, wow. 1/7. And so if we divide by 1/7, that's equivalent to multiplying by 7. So 7x to the 1/7, we're going to go from 15 to 160. So we want the area bounded by the marginal cost function and the x-axis. Let's see. 7 times 160 to the 1/7 minus 7 times 15 to the 1/7 is going to be what? I think it might not be $4.15, but let's see. Okay, $4.15. So the marginal cost, x to the negative 6/7, looks like what? A lot like the function that we had, but we go way out because we have to go 15 through 160. There's the 160, and then this one. And we need area all the way from 15 to 160. To 100, oh, sorry. It's not letting me grab the x-axis of the y-axis, come on. I don't know. It won't let me do that. From 15. And that won't go as high as 15 because of that slider, sorry. Too much. Why does integrating the marginal cost, finding the area underneath the marginal cost function, give us the total cost for these particular t-shirts? Let's see. Suppose we have c prime of x, but we need something nicer than this function. This was hard to read here. Let's go 1, 2, 3, 4. And as we produce more, hopefully the cost for each additional unit decreases. Now, in a case where the materials we're using are very scarce, as we produce more, maybe the cost actually increases. But hopefully it's going to decrease for us as we compare total cost to maybe the fixed cost. It's going to decrease. So suppose it's something like this. Let's say 10, and then down to we go 5 across, then we go 5 this way. Let's go simpler even than that. Suppose it doesn't decrease. Suppose it stays the same. That's our cost. That's our marginal cost. So at this point, when we're producing 0 units and C prime of 0 equals $10, what does that mean? That's the rate at which the cost is increasing for 1 additional unit. So what that means is if we produce 1 additional unit, we can expect our cost to increase by $10. Well, right here, C prime of 1 is 10. That means if we produce 1 additional unit, we're currently producing 1, and we produce 1 additional unit, we can expect our cost to increase by $10. All right, C prime of 2 equals 10. So same thing, if we increase our cost by 1 additional unit, we can, if we produce 1 additional unit, we'll increase our cost by 10. So if we wanted to look at the cost function, we could let the initial cost be anything. How much are you going to say it costs to produce no units? What's our fixed cost? Let's choose something that we can graph on this scale. I'm going to say our fixed cost, if we produce nothing, is $5. Maybe it's more like $5,000. I don't know what our startup cost is, but let's say it's $5. That's our fixed cost. If we, and I've got to shrink this down to put it on here, but I think I can do it. Based on the marginal cost that I have here, if we produce 1 more unit, we expect our cost to increase by $10 from $5 to how much? $15. Should I be more colorful than this? Let's go green there for the cost function. So the marginal cost is flat. The cost function is an antiderivative of that. We had a constant rule. If we want to take the antiderivative of 10, it would be 10x plus a constant, wouldn't it? So how about 10x plus 5? C of x equals 10x plus 5. So that's the cost function. So we're trying to get a handle on how much it costs to produce T-shirts 15 through 160. Suppose we're producing something here. How much would it cost to produce number whatever it is we're producing, widget number 1 through widget number 3? Widgets 1 through 3. If I've got this cost function and it's up like this. So that's the point 3. That's the point with x coordinate of 1. That's the point with x coordinate of 2. So I think that's 1, 15. This is 2, 25. And this is 3, 35. See, the disadvantage we don't have with this problem that we just looked at, and I got it from my MATLAB problem, is that we don't know the fixed cost. We don't have to know the fixed cost to know how much it costs to produce items 15 through 100, 150, 160, whatever it was. But we don't know the fixed cost. In this example, we do. We know the fixed cost is $5. But if we want to produce items 1 through 3, how much does that cost? Well, if we produce 3 items, it costs $35. But I think that's different from the area from 1 to 3. All right? What's the area from 1 to 3? That's going to be, for this function, 10 dx. Well, I don't need the integral there anymore. Yes, I do. It's going to be the integral of 10 dx from 1 to 3. It's going to be 10x from 1 to 3. It's going to be 10 times 3 minus 10 times 1, which is 30 minus 10, which is 20. So it actually costs us $20 to produce items 2 and 3, and that would be the total area from here to there. That's 2 items. See, my issue is with the left-hand endpoint of integration. I want to get that just right. So if it's how much to produce items 15 through 160, I'm concerned that 15 shouldn't be the lower limit, because here to produce items number 2 and 3, actually 1 should be the lower limit. Let me draw the picture for the one that we've been working on. Say there's 15 and over here somewhere there's 160. Figure not to scale. And the cost function, and there's and the figure's really not to scale when I put a 14 here. Not to scale at all. And we've got our cost function that's doing something like, this is marginal cost. Marginal cost is doing, so whoa, hopefully it doesn't come back up. Maybe it does if it gets scarce after a while. But something like that. This is y equals c prime of x, and the cost functions may be increasing. But I think if I want to know how much does it cost to produce item number 15, that's going to be this much. Because right here I've produced, this is how much it costs to produce items 1 through 14. I've produced those. And I just want to produce item number 15. How much does that cost? I think I need to integrate from 14 to 15. I think I do. Yes.
What would it look like if you were asking how much it would be from 1 to 15? Like, would it be?
Yeah, from 1 to 15 well, from 1 to 15 it would be this much. Yeah, that'd be from 1 to 15.
Yeah, but how do you know that they're just asking solely for 15? Like how much it is for unit 15?
Well, I was just asking that myself.
Oh.
I'm just trying to interpret this question here. The cost of printing the posters 15 through 160, basically we could figure this out by taking the cost of producing the first 160 posters and subtracting the cost of producing the first 14. I'm trying to, when you read this, when you just interpret it in plain English, I guess it's plain enough, does this include the cost of poster number 15? Is that the way you read that? We got to figure out, however much poster number 15 costs, that's included here. It doesn't mean, let's do the first 15 and then this is really, no, because I would say 16 through 160 if that's what I meant. This has got to include poster number 15. I think what we should have done here is this. I think what we should have done is scratch the 15 and put a 14. Now, the thing to do is go to my math lab, because as far as your grade is concerned, you want to make sure that my math lab agrees with whatever we decide. But I really think that should have been a 14 there instead of a 15 for the cost of producing these posters. So we'll go there in a little bit. Example 5. Company estimates that its sales will grow continuously at a rate given by this S prime of t equals 32 e to the t, where S prime of t is the rate at which sales are increasing in dollars per day on day t. Find the accumulated sales for the first 6 days. Accumulated sales for the first 6 days. Suppose we wanted the sales for day 1. Sales is an antiderivative of S prime. But we just want the sales for day 1. That would be the integral from 0 to 1. So if we want the accumulated sales for the first 6 days, I'm thinking we want from 0 to 6. So the integral of S, this is the A part, the integral of S prime of t dt, integrate this from 0 to 6. 0 to 1 is day 1, 1 to 2 is day 2, 2 to 3 is day 3, 0 to 6 is the accumulated sales for the first 6 days. And so this is the integral from 0 to 6 of 32 e to the t dt. Wow. Basically, e to the t is a high growth rate, growing rapidly. We can find an antiderivative for 32 e to the t pretty easily, simply by copying and pasting. 32 e to the t is one of its own antiderivatives. So substitute the 6, substitute the 0, and subtract. 32 e to the 6 minus 32 e to the 0, and crunch it out. 32 second ln 6 minus 32. Okay, so accumulated sales for the first 6 days, $12,877.72. The sales from the 2nd day through the 5th day would be the integral from 1 to 5. Again, 1 to 2 would be day 2, 2 to 3 would be day 3, and all the way up to 4 to 5, which is day 5. Same antiderivative, 32 e to the t. We're going from 1 to 5, so it's 32 e to the 5th minus 32 e to the 1st power. And must have been a lot of sales on day 6, because it's considerably less if we just add up day 2 through day 5. 32 e to the 5th power minus 32 times e to the 1st power. $4,662.24. We didn't care too much about the projectile motion problem at the end of class last time. Frankly, I don't blame you, but let's see if we can come up with the position function if we know the acceleration function and a particular value of the velocity function and a particular value of the position function. And kind of be nice if we could do something with a definite integral as an application of this. Well, if we have the position function, and if we were to take, we don't have the position function, we're supposed to be pretending that we don't see this right here, but hopefully it's the right answer, and hopefully that's the answer we'll get. But if we had the position function, and we take the derivative, we would get negative, for this one, 27t squared plus 6t plus 2. And this is the rate at which the location, the position of the particle is changing with respect to time, and another word for that is the velocity. Okay, if it's changing rapidly with respect to time, it's high velocity. If it's changing slowly with respect to time or just hanging out, it's low velocity. But it's the derivative of the position function is the velocity. If we take another derivative, v prime of t, that's going to be negative 54 t to the third power divided by, what am I doing? I don't know. What's 2 times negative 27? Maybe a better question for this, what's 3 times 3? It's been a long day, folks. I'm sorry. 3 to the third power is certainly 27, but that's not 3 times 3. That's 3 times 3 times 3. There we go. I'm trying to think, how am I going to get that negative 18? All right. 2 times negative 9. That'll give me the negative 18. Negative 18t plus 6. Wow. Okay. So this is v prime of t. That's the rate at which the velocity is changing. And the rate at which the velocity is changing, sometimes measured in, well, it doesn't give the units here, sometimes measured in feet per second, or meters per second, could be miles per hour per second. The rate at which the velocity is changing is the acceleration. So if we had the position function and we needed the acceleration function, we would get this. This problem gives us the acceleration function, and it wants us to work our way back to the position function. However, there are a lot of different position functions that might have gotten to the same spot. So we need the unique position function for the given information. So we start with a of t. V of t is going to be the integral of negative 18t plus 6 dt. So v of t is equal to negative 18t squared over 2 plus 6t plus some constant that we don't know, but we have enough information to find. V of t, I guess I need to simplify that to get negative 9t squared plus 6t plus c. We're given that v of 0 is 2. So that's enough information to find c. If we substitute 0 for t in both places where there's a t, the 0 basically zeroes out or eliminates the t terms, and we see that c equals 2. So v of t is actually negative 9t squared plus 6t plus 2. We needed this information to determine that that's a 2, because that could have been anything, and we would have taken its derivative and come up with negative 18t plus 6. But going backwards, we need something to tell us that's 2. So we had it. One more antiderivative. A of t equals the integral of negative 9t squared plus 6t plus 2. So a of t equals negative 9t cubed over 3 plus 6t squared over 2 plus 2t plus some other constant. You want to denote it with a different subscript, you can, or maybe we've just we put away that first constant, so this is a completely different constant. So what do we get? A of t equals negative 3t cubed plus 3t squared plus 2t plus c. How do we find the c? Plug in the 0. Use this initial condition, it's called. S of 0 equals 1. So if we substitute, wow, it's just been, actually it hasn't been that long a day. Maybe it's just been a long life. I don't know. Too many birthdays. TMB they call it in the math department. Too many birthdays. S of 0 equals negative 3 times 0 cubed plus 3 times 0 squared plus 2 times 0 plus c equals, what did it say, 1? Yes, glad I remember that much. 1, and that implies, after we evaluated the zeros, that c equals 1. So the position function that we get is actually negative 3t cubed plus 3t squared plus 2t plus, not c, the specific value of c that we got, 1. Nice enough. Going forwards, taking derivatives, going backwards with antiderivatives and initial conditions. What information could it give us if we integrate a velocity function? Well, we found, use the integral of this velocity function to define the position function. If we evaluate a definite integral of a velocity function, it gives us the change in position. Might not tell us where it started or where it ended up, or even how far it went, but it will tell us the change in position if we integrate the velocity function. I would hope we'd have an opportunity to do that, but we may not. We may not. That seems to be it. Let me go to my math lab problems. Oh, no, not there. Back. Maybe back from there. My math lab. So we have 4.1 and 4.2. We'd very much like to have some 4.3 problems to be working on. Nope, don't have any 4.3 in the mix. But if we look at it, we can say 4.3 area open until the 22nd, I think, because our test is the 23rd. Test is Tuesday the 23rd. Next. All right, 48 little questions. Definite integrals. What are we looking at? Oh, radicals. Radicals look good. Polynomial looks painful. Exponential looks good. Another polynomial. Another exponential. Hate to omit any of them. They all look so good. But these applications, find the profit when a well 200 feet deep is drilled. The marginal cost, given by this equation. Find the cost of printing 65 or more posters when 15 have already been printed. 65 more when 15 have already been printed. We did the poster problem, so that's a good one. And there's the velocity function and the acceleration function. It doesn't ask us to integrate it, though. Oh, there we go. Are you sad that I haven't given you more with the interactive figures?
No.
No? You're okay with that? Basically, I've just deleted them automatically. I look at them and say, oh, that looks interesting. Let's not do that. 23, that's still too many, huh? 23. I wouldn't want to do that many. So let's omit every other physics. And that one. And the second, business and economics. And 3 of those. 15? Is that better? You want too few because you want plenty of practice on this. 15. But I want to look at those physics problems. So let's look at this one and see if we can make sense out of this in the few minutes that we have. A motorcycle accelerates at a constant rate. Basically, that means constant acceleration, a of t equals some constant, from 0 kilometers per hour to 60 kilometers per hour in 18 seconds. Why couldn't it have just given us meters per second? Why did it have to give us kilometers per hour? I don't know. How fast is a motorcycle traveling after 18 seconds? I think we can do this without having to do the conversion. I'm thinking 60 kilometers per hour. Is it a joke? Yeah, it starts at 0, and at 18 seconds later, it's 60 kilometers per hour. So after 18 seconds, it's 60 kilometers per hour. And it even agrees with us, 60 kilometers per hour. Okay, so that wasn't too bad. How far has the motorcycle traveled after 18 seconds? That's the more challenging question. And yeah, we should convert seconds to hours, and I guess leave it in kilometers per second. No, leave it in kilometers. Leave it in kilometers if we convert to convert seconds to hours. Great. So 18 seconds. How many seconds in an hour? So 3, 6, 0, 0. Is that it? 60 times 60? Whatever that is. 3,600 seconds. So this is going to be 18 over 3,600. Or about, divide them both by 18. 18 seconds is 1/200th of an hour, I think, maybe. Strange way to interpret that. I'd much rather deal with seconds than hours, if it's such a small fraction of an hour. But what we want to do is integrate the acceleration function know how to integrate the velocity function. What is the velocity function? Because we want to find the position. We need to integrate the velocity function for the position. So A of t equals, well, what is, we're going from 0 to 60 in 18 seconds, so that's how many kilometers per hour per second? What's 60 divided by 18? Divide them both by 6, I guess. Maybe divide them both by 6. 10 over 3. So 10 thirds kilometers. Sorry about that. Kilometers per hour per second. So so v of t this might be a good time to stop. The computer is suggesting